The free response question, number 12, we have f as the function defined, it's a piecewise defined function. It's the square root of x plus 1 for the domain of 0 to 3. It's a closed interval. And then the function 5 minus x for x greater than 3, less than or equal to 5. First thing we have to do is show that f is continuous at x equals 3. Okay. Way back at the beginning of the course, we talked about continuity and the 3 requirements. The first is that the function must exist at 3. So f of 3 exists. And we know this because we see that symbol right there. So the 3 is part of the domain, and f of 3 is equal to the square root of 3 plus 1, which is equal to 2. Our second requirement is that we show that the limit of the function as x approaches 3 exists. Okay, in order for our limit to exist, the limit from the left must be equal to the limit from the right. So the limit as x approaches 3 from the left, and remember from the left is the superscript negative symbol of our function, that has to exist. And in fact it does, because we're talking about numbers just below 3. So again, numbers like 2.999999, which means we're plugging them into this top function. But again, those numbers are so close to 3, we can basically generalize with the 3, so we get 2. Now we have to check out the limit as x approaches 3 from the right. So that's numbers like 3.001. Alright, and those numbers are slightly above 3, which places them in this range right here, which means we have to plug it into the bottom function, 5 minus x. Again, the number is so close to 3 that we can just use 3 as the value, so we replace x with 3, and we get 2. Alright, so therefore, we know that the limit as x approaches 3 of f of x exists, alright, because the limit from the left was 2, the limit from the right was 2, okay, and equals 2. And then our third requirement is that the value of the function, which is 2, must be equal to the value of the limit of this x approaches the number of the function, which is also 2. So we have to write down 2 equals 2, and now we've got all 3 requirements done. For part B, we have the integral from 0 to 5 of f of x. Well, the piecewise defined function, the cutoff point is at 3. So we have to break this up into 2 integrals. It's the integral from 0 to 3 of f of x dx, plus the integral from 3 to 5 of f of x dx. And the idea being is that our cutoff point, 3, in other words, our upper bound for the first integral, is also our lower bound for the second integral. So where this one ends, this one picks up. And we get our entire range of 0 all the way to 5. And again, the reason why we're doing that is because when x is equal to 3, we're changing functions. Okay, before 3 we have to use the square root of x plus 1. After 3 we have to use 5 minus x. Just going to scroll back up, and I'm going to replace those. Okay, so for 0 to 3, we have the integral, and it's going to be square root x plus 1, because that's the function we should use over the domain from 0 to 3. For the domain from 3 to 5, we have to use the bottom function, which is 5 minus x dx. Okay, so we have to do a fundamental theorem of calculus for both of these. All right, now x plus 1, square root of x plus 1, keep in mind that's equal to x plus 1 to the 1/2 power. which I believe we took care of earlier in the study guide. We know that because we have something ugly to the 1/2, but u being x plus 1, du would just be dx. So we don't have to really do u substitution here. We can just treat this as the antiderivative of our x plus 1 to the 1/2. So that's going to be x plus 1 to the 3/2 over 3/2. And that's evaluated from 0 to 3. Next to that, we have to do our antiderivative of 5 minus x. Well, 5's antiderivative is 5x. X's antiderivative is x squared over 2. And that's being evaluated from x equals 3 to x equals 5. Now right here, we have dividing by 3/2, which is the same thing as multiplying by 2/3. And then we have x plus 1 to the 3/2. That's the square root of x plus 1 being cubed. Okay, so we're going to plug 3 into this first. So we have 2/3, and then we have the square root. 3 plus 1 is 4, so it's 4 cubed. Then we have to plug 0 in next. Now when we plug in 0, we don't get 0. Okay, we get 2/3, and then 0 plus 1 is 1, so we have the square root of 1 cubed. That's the fundamental theorem of calculus working on this first part. Now we're going to add to that. Now we have to plug 5 and 3 into this second integral, using the fundamental. So we have 5 times 5 minus 5 squared over 2. And we're going to subtract 5 times 3 minus, actually let me use parentheses here just to, there we go, minus 3 squared over 2. Okay, now, it's a free response question, so we are done. We don't have to go any further than that. We've evaluated, we've done the fundamental theorem of calculus, we haven't simplified this, we don't need to simplify this. You can go ahead and simplify it, but it's not necessary. You've performed the fundamental theorem of calculus, and this is a correct answer. Finally, with part C, okay, so we have this g of x function, which is similar to f of x up at the top of the page, except we've got k and m. And the question is now, if k and m are constants, g is differentiable at x equals 3. What are the values of k and m? Okay, so we have two things at play here. First of all, if g is differentiable at x equals 3, then we also know that g is continuous at x equals 3. Okay, what does that tell us? That means that if we plug 3 in for x, these two have to be equal to each other, because if the function is continuous, where the top function stops performing, the bottom function must pick up at the exact same spot. Alright, so what we're basically saying for the continuity part is that k times x plus 1 must be equal to mx plus 2 when x equals 3. Okay, so if we replace 3 in for x, we have k times the square root of 3 plus 1 is 4. And then over here we have m times 3 plus 2. So just simplifying this slightly, we see we have twice k is equal to 3m plus 2. Now our goal is to figure out what k and m are equal to. Right now we have one equation with these two variables. It's impossible to come up with, well, it's not possible, but there's multiple answers to this. We want one value, which means we need another equation, where in essence we're putting together a system of equations. So to get our second equation, we go to the idea that g is differentiable at x equals 3. If g is differentiable at x equals 3, that means that if we derive both of these and plug in 3, they'll be equal to each other. It's like doing the same thing that we did over here, except not at the original level, but down at the derivative level. So we need g prime. Right? When you have a piecewise defined function, you just derive the top and leave it, derive the bottom. So in other words, the derivative of mx plus 2, that's just going to be m. So g prime is just going to be m when x is between 3 and 5. Right? Now when x is between 0 and 3, we have to do the derivative of this up here. Okay, well this is k, and then we have x plus 1 to the 1/2. So when we take our derivative, we have 1/2 out front, then we have our k, and then we have x plus 1 to the negative 1/2. Okay, and to kind of rewrite this, it's going to go right in there. So we have a fraction. We have 2 down at the bottom. We have k, that's our 2 right there, down here. Here's our k, that's up top. And then we have x plus 1 to the negative 1/2 power, which means it's x plus 1 to the positive 1/2 power once we move it into the denominator. And 1/2 power is the same thing as square root. Okay, so what does that tell us? It tells us that k over 2 times the square root of x plus 1 will be equal to m when x equals 3, because g is differentiable at x equals 3. So if we plug 3 in for x, we have k over 2 times the square root of 4 is equal to m. Square root of 4 is 2, 2 times 2 is 4, so that means that k over 4 is equal to m. Since I'm not a big fan of fractions, I'm going to basically just change this. I'm going to multiply both sides by 4, and k is equal to 4m. Now I've got a system of equations. K is 4m, and 2k is 3m plus 2. So let's do some substitution. I'm going to replace k with 4m. So I have twice 4m is equal to 3m plus 2. So 8m equals 3m plus 2. Subtract 3m from both sides. 5m is equal to 2. And so m is equal to 2/5. K is 4 times m. So k is 4 times 2/5, or 8/5. Right. Now, this is a nice review from earlier in the year, as is Part A, but the key to this problem as far as getting ready for the test is the piecewise work that we did here in Part B.